Hi everyone, I'm Shan Jiang from Northeastern University. This talk is about a work I did during a summer internship at Google. This is a joint work with Simon Baumgartner, Ittycheriah, and Cong from Google Research. The title of the presentation is Factoring Fact Checks, Structured Information Extraction from Fact-Checking Articles. Let me start by introducing the terminology we used. So fact checks, what is it? The first sentence on Wikipedia gives us a pretty good understanding of what it is. Fact-checking is the act of checking factual information in non-fictional text in order to determine the veracity and correctness of the factual claims in the text. To simplify it, fact-checking is just the act of checking facts, and we call an article that does fact-checking fact checks. Here is an example of a fact check. This is a fact check published by PolitiFact titled "No Newspaper Isn't an Acronym for Northeast, West, South, Past, Present, and Event Report." And it goes in depth about the origin of the claim, how it is spread, why it is false, etc. This is a very well-written article and tells its readers about every detail about this story. But nowadays, a lot of people are on a too long don't read agenda, and we sometimes prefer to get the key information as fast as possible. In fact checks, there are three important what we call factors that summarize the main message of the fact check. The first is a claim. In this case, the claim is newspaper is an acronym for something. The second is a claimant, which is a person or organization who made the claim. In this case, a viral Facebook post. And the last one is a verdict, which is the rating of veracity of the claim. In this case, it's rated as pants on fire, which is the lowest rating of veracity given by PolitiFact. With these three factors identified, we can summarize the key information of the fact check. Another advantage of these factors is that they are relatively structured information that can be understood by algorithms, therefore enabling web applications using this information, such as search engines. For example, in Google, if we search newspaper acronym, Google returns the first result as a structured snippet of the fact check, which contains the claim, claimant, and the verdict. The similar result is returned by Bing, except that it's another fact check from Africa Check instead of PolitiFact. Hopefully, I convinced you that these factors are useful, but the question is how to get these factors. Traditionally, journalists use creative language to attract users, therefore hiding these factors within the fact checks. One way to get these factors is through self-reporting using a tool developed by Google, where fact checkers go to this website, submit an URL of their fact check, enter the claim, claimant, and the verdict, and submit this data to Google for better visibility. Another similar way is to use a claim review markup, which is a JavaScript snippet to embed in the HTML content of a fact-check web page. The problem here is that it takes time to manually input these factors, and it distracts journalists from their main job of investigating the claim. As a result, Duke's Reporters Lab reported that less than half of fact-checkers have adopted this schema as of July 2019. So in order to save time, we propose factoring fact checks, a task of automatically extracting these factors from fact checks. We take two steps for this task. In the first step, we explore existing fact check data to understand the patterns of factors. And in the second step, we experiment with information extraction models to actually extract these factors. And hopefully, we can use some knowledge from the first step. Let's start with the first step. The data we used is a public fact-check dataset from Data Commons. And we currently focus on English articles only, which leave us a little more than 6,000 fact checks to explore. Each of these fact checks are associated with their reported factors, including claims, claimant, and verdicts. So, the first question we ask is, who are the fact checkers? This figure shows the distribution of fact checkers of totally 27 fact checkers in the dataset. It's kind of a power law distribution where the top 5 fact checkers, which is roughly 20% out of 27, published more than 90% of fact checks, We refer to the top 5 fact checkers as well-known ones, as they are famous organizations that are heavily focused on fact-checking efforts. So PolitiFact, factcheck.org, and the Washington Post are American-based. Factly is from India, and the last one is Africa Check. The rest of the 22 fact checkers are underrepresented in the dataset. These fact checkers could be newly established fact checking teams or well known news agencies doing occasional fact checking, etc. This observation will affect our experimental design later. Let's move to the next question. Can factors be found in the fact checks? Our task is to extract factors from fact checks. So if factors are not in the fact check, then this task seems to be unachievable. We start with exact string matching between the reported factors and the fact checks. We found that although most claimant and verdicts can be found in the fact checks, we can only find 1/3 of the claims. The reason here is paraphrasing. Consider the previous example. The claim in the article is newspaper is an acronym for something, while the reported claim paraphrased is an acronym for to stand for. In order to match more claims, we developed a fuzzy matching rule. Specifically, we find the matches that have at least 2/3 of the word overlap, and then use a minimum window substring algorithm to find the match. Note that a factor may appear more than once in a fact check. Using this fuzzy matching rule, we are able to find near 80% of claims at least once in fact checks. Similarly, the number of matched claimant is 80%. And the number of matched verdict is also 80%. This observation suggests that most factors can be roughly matched in the fact checks, therefore providing some feasibility of our task. Finally, we ask the question, if factors can be found in the fact check, where are the factors? We use a relative position measure to answer this question, where we simply take the position of the factors and then divide it by the length of the fact check. This gives us a number between 0 and 1, where 0 means the head of the fact check, and 1 means the tail. We also look at this question separately for well-known and underrepresented fact checkers, because they may have different distributions. First, we look at the claims. The dashed line shows the distribution of relative positions for well-known fact checkers, and the claims are distributed at both the head and tails of the fact check. The concrete line shows the distribution of relative positions for underrepresented fact checkers, and the claims are distributed at only heads of the fact checks. This is because fact checkers started their article by introducing the claim, but only well-known fact checkers have a recap section in the end. For claimants, the distribution is similar between well-known and underrepresented fact checkers. As shown in the dashed and concrete lines, they are both heavily distributed at the heads of the fact checks. For verdicts, the distribution for well-known and underrepresented fact checkers are different. For well-known fact checkers, they usually introduce their verdict at the recap section, which is at the very end of the fact checks. Here, they also like to use their specialized words, such as Pants on Fire from PolitiFact and the Pinocchio system from the Washington Post. Such recap section and specialized verdict system do not exist for most of the underrepresented fact checkers. So most of them just introduce their verdict in the beginning, such as someone made a false claim, or this is a true claim, etc. So overall, this observation suggests two things. The first is that most factors are in the heads and tails of the fact checks. And the second is that well-known and underrepresented fact checkers have different distributions. Similarly, this observation would be useful for later experiments. So we answered some basic questions of the dataset, and now we get to the second part, which is to experiment with information extraction models. The intuition behind running these experiments is that there are certain linguistic patterns when a factor appears in the fact check. If we look at the factors per se, the language used by claims are mostly factual sentences, and sometimes contains numbers, statistics, etc. Claimants are mostly person or organization. Verdicts are mostly adjective words or phrases that describe veracity, such as true, mostly true, false, etc. or phrases from specialized verdict system, such as Pants on Fire by PolitiFact and the Pinocchio system by the Washington Post. In addition, we could also look at the surrounding context of the factor. Claims usually appear following certain verbs as context, such as someone claimed, someone said, etc. And we can also identify claimants from this context, which is someone. Verdicts are often explicitly pointed out by a concluding sentence, such as we rate this claim true, or it could be embedded in a sentence such as a false rumor claims, etc. This intuition gives us some confidence that we can use NLP models to extract these factors from fact checks. We formulated the task as a sequence tagging task, where the input is a fact check as a sequence of tokens, and the output is an equal-length sequence of labels. Consider this example. If the input is John Doe made a false claim that the Earth is flat, then a potential output would be labeling the first token's John Doe as a claimant, the fifth token false as a verdict, and the last token the Earth is flat as the claim. Recall that fact checks and its reported factors are available in our dataset, but factors can be paraphrased. Therefore, we need to find a way to generate ground truth token level labels for the fact check. To generate ground truth labels, we develop two rule-based taggers for the task. A fluent tagger that tags indexes of the entire span of matched factors, and a concise tagger that tags the index of only the overlapping part. We added some additional words to the previous example for illustrative purposes. If the sequence is John M. Doe made a false claim that the Earth is actually 100% flat, and its three factors are the Earth is flat as a claim, John Doe as a claimant, and false as a verdict. The fluent tagger labels John M. Doe as a claimant and all words starting from the Earth as the claim, while the concise tagger skips non-overlapping words M for the claimant, and actually 100% for the claim. Intuitively, the fluent tagger is focused more on readability as it generates continued phrases as ground truth, but it also inevitably includes unessential details in the sequence. On the contrary, the concise tagger is focused more on brevity, as it only selects essential words of factors, but the results could be less readable if matched factors miss several words. To run our experiments, we first consider some trivial baselines. For claims, we use a popular system called ClaimBuster, which scores the checkworthiness of sentences in the article. The hypothesis is that fact-checked claim might also have the highest checkworthiness. For claimants, our intuition is that claimants are most likely to be a person or organization, and they are also likely to be heavily mentioned in the fact check. So we run our fact checks through a named entity recognition pipeline and label the most frequent person or organization as a claimant. For verdicts, we take a simple approach of majority voting from the training data. The expectation here is that trivial baselines should not have a good performance on our task. Otherwise, our task is also trivial. Next, we experiment with BERT. BERT is a state-of-the-art model for a wide range of NLP tasks. It is basically transformer neural networks that follow a pre-trained fine-tuning process. During the pre-training process, BERT is trained to predict missing words in a large corpus, and in doing so, adjusting the parameters so the model can have a general understanding of human language. Then, during the fine-tuning phase, we replace the last layer of BERT with a tagging layer, and calculate the cross-entropy loss of the token level to retrain BERT for our tasks. One specific design of BERT is that it has a maximum sequence length of 512. Considering that fact checks are usually long articles, we need to feed fact checks to BERT paragraph by paragraph. This leads to a new concern that our model can only use information of the input sequence per se, but cannot have a global view of the entire fact check. So we want to try to add some external information to the process. Recall that our previous observations show that most factors are in heads and tails of fact checks. Based on this observation, we made a simple modification to BERT. So the vanilla BERT model used CLS as the lead token to represent the start of the sentence. We replace it with a paragraph position token, which could be either head, body, or tail, to represent the relative position of the paragraph. We also associated these tokens with 3 corresponding labels in the output sequence. We expect this modification can help BERT model to learn better representations for each paragraph based on its location, and therefore improving the ability to tag factors in the paragraph. Another observation we had is the power law distribution of fact checkers. And because the distribution of fact checks between well-known and underrepresented fact checks are different, which suggests that models learned and evaluated by using all the data would mostly reflect the performance for well-known ones. To understand the performance of models on both well-known and underrepresented fact checkers, we split our data in the following ways. First, we keep the fact checkers from well-known fact checkers and do a 80-10-10 random split to train, develop, and test sets. Second, we use the remaining fact checkers from underrepresented fact checkers as a second test set. This test set is used for evaluation only and invisible during the training process, which allows us to understand how models can generalize across different journalistic styles. For the evaluation of model, we use root scores, which compares overlap between the ground truth and the predictions. Note that if the prediction is empty, which means that no factors is tagged, then all F1 precision and recall root scores are 0. This is a tight score for evaluation. So depending on specific applications, sometimes we only care performance when our model does tag something. Therefore, we also introduce a loose score that counts only when something is tagged. So in the results section that I will show in next page, there are 2 scores in a cell. The first number is a tight score and the second number is a loose score. So now we can look at the results from our experiments. Note that all these results are trained from well-known fact checkers, and then predict factors of a test set which is also from well-known fact checkers. The first observation is that baseline methods has a very poor performance, which means that it is not a trivial task that we are trying to solve. The next thing we observe is that we have significant improvement of performance with the vanilla version of BERT. Just to jump the process a little bit, we have further improvement of performance with our modified version of BERT with paragraph tokens, which makes it the best performing model. For claims, the best model achieves tight F1 score around 0.65 and a loose score around 0.85. This means that although the model is sometimes not tagging, when it does tag something, the results are reasonably good. The numbers are higher for claimants, which has a tight score around 0.8 and loose score around 0.9, which means that the model is pretty good at finding claimants. We get the highest number for verdict. Both tight and loose scores are above 0.9, which means that the model is really good at finding verdicts. So overall, the results looks pretty good for well-known fact checkers. So now we want to look at to what extent our model can generalize to underrepresented fact checkers. Note that all these results are trained on well-known fact checkers and then predict the factors of underrepresented fact checkers, which are completely invisible during the training process. As the table shows, the performance of our model drops. The modified BERT model with paragraph tokens is still the best model overall, so we look at some of its performance. So the scores for all factors systematically drops in this table. The tight F1 score are somewhere near 0.4 to 0.5, and the loose scores are near 0.7 to 0.8. This means that because of different journalistic styles between well-known and underrepresented fact checkers, our model has a hard time to generalize. We also explored some possibility to improve generalization by mixing half of the underrepresented fact checkers to the training set. Our results show improved performance for tagging claimant and verdict, but not improved for tagging claims. Note that in this process, we only added around less than 200 samples to the training process, so we are not expecting a huge difference of performance. Finally, we qualitatively look through some cases when our model makes mistakes. And there are some common patterns that we could summarize. The first is not tagging, which happens for unseen patterns, such as very long verdict with explanations instead of just a verdict such as true or false. The second is wrongly tagging something, which is probably the worst case. This happens for confusing patterns. For example, there are well-organized sentences in some fact checks like someone claimed something on some date, but this is in fact not the claim. This type of patterns can easily confuse our model. The third error is partially tagging, which happens for some unusual patterns. For example, some fact checker reports the claimant as the 45th and current president of the United States, Donald Trump, while our model tends to tag only the name part of Donald Trump, which results in a low root score. So to summarize, our experiments show the overall feasibility of the task factoring fact checks, especially for well-known fact checkers. However, as this task directly faces the misinformation problem, we need extremely high accuracy to fully automate this process. Therefore, our primary application of this task is kind of a human-in-the-loop process that can benefit from our models. For example, as mentioned earlier, current journalists can submit their factors through a markup tool. Our model can be used to pre-populate these factors after the user specifies a URL. And then later a user can check our pre-population, revise them if needed, and finally submit to save them some time. To conclude this talk, we proposed factoring fact checks, a task of automatically extracting the claim, claimant, and verdict from the fact check. We explored an existing dataset and showed some high-level observations of the distributions of factors, such as most of them can be found in the fact checks, especially in the heads and tails of the fact checks. We experimented and modified the state-of-the-art BERT model for information extraction and demonstrated applicable performance for well-known fact checkers. And finally, although our model has difficulties generalizing to underrepresented fact checkers, we show some promising initial results on this front. Our hope is that this work can play a role in the progressive process of leveraging fact checks to improve information quality online. Pre-population tools with the help of our models can encourage more fact checkers to provide factors, which in turn can serve as training data to further improve the performance of our models. Okay, that's all. If you have questions, please feel free to send them to my email address here. Thanks for listening.